Hello everybody, welcome to part 4 of our Unit 3 Sensation and Perception unit. Today what we're going to be talking about is all of the other senses other than vision. So we've talked about vision, we've talked about the perceptual aspect of vision. Today what we're going to be doing is looking at our other senses. We're going to start with hearing, then we're going to also talk about things like taste, smell, touch, and our other bodily senses as well. So like I said, we're going to start first with hearing. We're going to have the most depth in our auditory sensations or our hearing sense behind, just behind vision. And the other ones, we're only going to spend about a slide or two on the rest of them after that. So the first kind of big question here is, how do we hear? What is actually happening? So there's a few kind of pieces that we need to know just to get the groundwork. And one of the terms is just audition. Audition is just the biological process by which our ears process sound waves. Okay, so it's basically just the process of hearing. It's just really important if you hear, look at audio is obviously where that word is coming from. But it's just important to see this term. That way when it pops up here and there, that's what they're talking about. Okay, it's that transduction, or it's how our ears are, again, turning sound waves into something meaningful, how they process it. So from there, the next question is, okay, well, what is a sound wave then? So a sound wave is literal molecules that are vibrating through the air. So basically what's happening, and we'll see a slide, I think it's actually the next slide, or in a few slides we'll see one. What's literally happening is there's, obviously in the air you don't necessarily feel anything, but there is stuff there, right? There's a bunch of different molecules and atoms and things floating around. And so what happens is that sound is literally waves in all of that air, and all of the molecules that are making up the air. So those different things are basically running into each other and is creating waves or ripples, kind of like you would on top of maybe a pond. So what's happening with sound waves is those are then basically hitting into each other, and they are then moving outward from the source. So as I speak, or as you listen to me speak from your laptop, the speakers are producing sound, and that sound is then rippling out from that place. Now, there's a few kind of other things that are important. So one piece of terminology that you're going to want to know is a medium. So vibrations are going to move in what is called a medium. A medium is just whatever the vibrations are moving through. So generally speaking, when we're talking about sound, the medium is air, because that's usually how we speak. Technically, it could be really anything though. So for example, when you're underwater, you can still kind of hear things. If you yell underwater, you can still kind of hear it. It's still moving. It just doesn't move as well through the medium of water as it does through air. At least our voice doesn't. So it's going to be moving through this medium outward from the source. So like I said, again, we're going to have this central point. So as you speak, that's going to be your mouth and your vocal cords. If it's a speaker, it's going to be that main piece of your speaker in your computer, and it's going to start at that source, and then it's going to go outward from there. And again, what's happening is it's compressing these molecules, and then they're letting them move apart. So as I speak, right, those molecules are literally being compressed and then moving apart, and it's causing this wave or this ripple that will then travel through the air. That's why, for example, when you talk, the more walls that are in between you and somebody else, the harder it is to hear you, because those walls are basically barriers that are stopping these waves. Okay, that's something we can kind of talk about there. So let's kind of talk about the waves themselves. So now that we kind of have an idea of what they are, how do we describe them? How do we talk about them? So one of the big things that we have to talk about is what is called amplitude. Amplitude. Now, amplitude is the height of a wave. So a sound wave is going to look very similar to like our electromagnetic wave. It's going to look like a wave. So amplitude is really important. Again, it is the height of the sound wave. So how tall or short is it? And what amplitude is going to do is determine how loud a sound is. Now, we measure sound in decibels. So it's basically how many decibels is it? What is the loudness? Here you can see a nice little decibel scale. Oops, sorry, I kind of covered up the bottom there. From 0 decibels to 110 decibels. Now, this scale is made for human beings, basically. So 0 is the threshold of human hearing. So anything below 0, human beings cannot hear. Now, obviously, there are still sounds at levels that can, I guess, technically be lower than that, but we can't pick them up. We can't hear them. So if you look at it, we've got at 10 decibels is quiet breathing, 20 decibels is a quiet room. If we move up to 50, that's a normal conversation. Up to, let's say, 80 is a loud radio, 90 is a bass drum, 110 is some sort of like industrial noise, so like heavy machinery. 120 is a jet plane taking off, 130 is a gunshot or maybe like a really loud concert. So you can see these kind of differences in how we can measure. And again, it's all about that amplitude of that wave. How tall is it? Now, decibels that are at 120 or higher, so right here about this jet plane and above, can cause immediate damage to one's hearing. So there is basically, and we'll see this, of how the ear is actually made, but we can damage our ears very easily actually through very loud noises. This is why if you've ever been to an airport, if you've ever been on a plane and you look out at all the people working on the runway, they all have, the big headphones, right? And obviously they can communicate through those, but also it's very important because it is blocking out all of that extra sound. Same thing with people that work construction or that work in very large areas, is we are protecting our ears from basically all these decibels. If we get something that's at 150, it will actually rupture your eardrum. So it will literally rip the membrane that is your eardrum, and you would lose your ability to hear there. So we can definitely damage these things pretty easily, actually. So continue to talk about waves here. So we've mentioned that amplitude is, how tall it is, and it has to do with the how loud something is. But there's obviously a lot more to do with sound than just how loud it is. So we also specifically have to talk about frequency. So frequency is the number of wavelength cycles in a unit of time. We measure it using hertz, and it determines the highness or lowness of the pitch of a sound. Okay, so here's some examples. Where's my mouse? Here we are. Here's some examples of some waves here. And what we again would be looking at is frequency. Now, there's two things that are really being measured here with frequency. There is the number of wavelength cycles, right? So it's basically how far apart are our highs and our peaks is what I want to say. I'm sorry, our peaks. So we got one peak. Obviously, you can't see the next one here, but our next peak. So we would measure that, and that's going to be our frequency. How quickly are these going by? Now, again, what this is going to do is determine our highs or lows, so the tone or the pitch of a sound. So when you speak really high, that's going to have a higher frequency. When you speak really low, that's going to have a lower frequency. So we can kind of see a few different measurements here. So humans perceive the range from 20 hertz to 2000 hertz. So again, our ears don't pick up everything. There is a range that we can go to. This is why something like a dog whistle works, and you blow it and maybe you can kind of hear it a little bit, but it's not super loud, or sometimes you can't really hear it at all, but your dog picks it up really easily. Basically what you're seeing there is actually there is a frequency that is too high for us to hear. So it's above that 20,000 range, and so because of that, your ears aren't able to pick it up, but your dog's ears are, because they're much more sensitive to pitch than ours are. They're able to hear those. So again, the shorter the wavelength, again right here, the shorter this is, the higher the frequency, and the higher the pitch. Which should probably make sense, right? The longer obviously these are, the longer the shorter, the less the frequency is, because obviously if it's really long, you're not going to get as many cycles. If it's very short, you're going to get a lot more cycles. So shorter wavelength means higher pitch. Means higher frequency, which means higher pitch. A longer wavelength, and here's what we have like here, longer wavelength is going to be a lower frequency and a lower pitch. Sorry about that, I know it's covering it up at the bottom there. And again, here's these examples. So they can talk about being quiet versus being loud. This is amplitude, so this one's shorter than this one. We can talk about being longer is deeper, and being shorter is higher pitched. I'll mention one more thing. The pitch, amplitude is involved as well, obviously, but the pitch is also important for how it travels. So this is why you can hear like bass from really, really far away, and it travels really well and goes through things better, is because of the wavelength. Because of the way the wavelength is made, it actually travels better and it goes further, which is why, like, if you hear somebody driving down the street, you can hear the bass, and then they come like 30 seconds later or something like that, and then you'll be able to hear the high-pitched sounds. So let's start talking about some of these parts. Now that we have these ideas of, okay, what are we actually collecting? What information are we picking up? How are we doing this? So there's a few different parts. Our first one is our pinna. Now, this is the visible part of the ear. It's right here. Now, sometimes, and I just covered it up again, they'll also refer to this as the auricle. You can see that at the very bottom. I'm not going to move my mouse, otherwise it'll block it for you again. But it's also sometimes referred to as the auricle. Really, those are the main two words you'll hear. Sometimes they'll use like another. Sometimes there's even like 2 or 3 other ones, but those are the 2 big ones. These, for the most part, aren't hugely important for our conversation because it's really just the outer part of the ear. It's the part that you hear. It's the part that sticks out of your head. So you should probably be able to figure out pretty easily what it is most of the time, and there are not a ton of questions about it usually. Now, as you could probably maybe even guess just from your normal life and going around, is that all that this is doing is collecting information. So it's collecting sound waves and kind of like funneling them into your ear canal. So similarly to how our cornea is bending the light into our pupils so we can see, our pinna or our auricle are going to be kind of like collecting sound to then funnel it into our ear canal. This is also why, for example, when you can't hear something, you go like this. You cup your ear. Again, what you're doing is you're trying to collect that sound again. So when I go like this, I basically am making my pinna or my auricle bigger, and I'm able to then collect more energy or more information as I listen and hear better. Next, we have our tympanic membrane. So our tympanic membrane is just the technical term for the eardrum. So again, here's our auricle or our pinna here, right? It collects, these are our sound waves, these kind of like little smoky looking things, right? It's coming in, and then what they're going to do is they're basically going to run into the tympanic membrane. And again, this is just the eardrum, so you can see it right here. Now, the eardrum is called the eardrum because it looks just like a drum. So it's a flat surface that's basically like, it's obviously like made of flesh, but it looks like an eardrum. It looks like a membrane over the top of it. Right, it looks like a membrane. And what's going to happen is as those sound waves come in, they're going to basically run into that eardrum, and they're going to cause the drum to vibrate. So just like an actual drum works, and when you hit a drum, right, the membrane on the top vibrates, the same thing is going to happen with our eardrum. Okay, so that sound's going to hit it, it's going to cause it to vibrate. So those are our first 2 parts. These are, generally speaking, considered like, usually the pinna will be considered the outer ear. Sometimes the eardrum is outer, but it's really more closer to the middle ear, and then there's also an inner ear. So we'll talk about each of these. So let's talk a little more specifically about the middle ear. And this is where things can get a little bit more complicated if you haven't heard this before. So again, we still do have our eardrum. Sorry, I'm like in the way a little bit here. Let's do that. Okay. So again, here's our eardrum from the inside. Here it is right here. Here it is right here. There's 3 different images of it. There's our eardrum. So again, what's happening, the sound is coming in and it's basically running into that membrane, and it's causing that membrane to vibrate. What's going to happen is that membrane is then connected to the bones of our middle ear, or our inner ear bones. So basically, when it hits that eardrum, it causes these bones to vibrate, which causes the next bone to vibrate, which causes the next bone to vibrate, and on and on. Okay, so that's how it's getting from our eardrum through the bones of our middle ear. So what those bones are called, there's 3 of them. There's the malleus, or the hammer, the incus, or the anvil, and the stapes, or the stirrup. Okay, malleus, incus, stapes, hammer, anvil, stirrup. So let's look at this example here. So this would be the hammer. Here is our anvil. You can think of kind of like if they're, whoops, I clicked the wrong button, sorry. You can think of like if they're not actually hitting each other right here, but if it was, you could think of how this would be, looks a little bit like an anvil. This can maybe look a little bit like a hammer. And then here's our stirrup. Our stirrup is the only one that actually looks like a stirrup in my opinion. So that one's usually the easiest to remember. So again, what these are just basically tiny, tiny, tiny little bones. And what they do is they actually concentrate those vibrations. So the membrane starts vibrating just like this. And then as it moves through these bones, these vibrations basically get like concentrated. They get concentrated into a certain spot. So instead of vibrating over this whole membrane, now they're focused into these tiny little bones. And really all that's happening is those vibrations are getting passed through. From there, we move to our inner ear. And I'm right in the way right now. And let me maybe go back 1 second so you can see I'm a little bit in the way again. Right here, you can see our stirrup. So our inner ear is this next part right here, or right here. It kind of looks like a snail. It's got a little shell, and there's all these little tubes sticking out. Okay, that's our next part. That is our inner ear right there. Okay, so the inner ear. So the main part of the inner ear is the cochlea. That's the most important thing for us. So what the cochlea is this coiled, bony, fluid-filled tube. So that's the shell that I just showed you on the last slide. It looks like a snail shell. And again, you can kind of think of it almost like that, a little shell, but it's filled with liquid. It's filled with fluids. And what happens is when the stirrup is vibrating, it causes waves in that coil, in that shell. Causes this fluid to wave. And so this is why I put this GIF right here. Obviously, this isn't your inner ear. This is a wave pool, but it's kind of a similar idea. Now, obviously, this would be closed. You wouldn't have like a ton of extra space floating around in there. But when that stirrup moves around, it then moves the liquids inside of the cochlea. So this is kind of what's going on. So here's our cochlea inside. Now, if you can imagine, inside of the cochlea, there are a whole bunch of little tiny hairs. So you can kind of think of them in our example of what we have right here for this GIF. Maybe like if there was a bunch of little pool noodles that you glued to all the walls of this wave pool. And what those are called are the organ of Corti. The organ of Corti. So what these are all these little tiny hair cells that are basically going to be moved. Obviously, they're in the liquid. So when that liquid goes through, it causes them to move around just like a pool noodle would in this pool. And they are actually what is going to do the transduction. So they are actually going to turn that movement into the nerve impulses. Now, you don't have to talk about specifically how that happens. That's kind of beyond us and what we're going to do in this class. But that's the gist of it. So I'm going to go through it one more time really quick. I'll go to the beginning. So again, these vibrations of sound come from outside of our body. They go in, they get collected by our outer ear and funneled into our ear canal. They then run into our eardrum, which will vibrate. Those vibrations then get passed through the malleus, which is the hammer, the incus, which is the anvil, and the stapes, which is the stirrup. From there, they are concentrated, and that stirrup will move the fluids that are in the cochlea. The movement of the fluid will then move the hair cells, or the organ of Corti, which is inside of the cochlea, which then turns all of this information into a nerve impulse or a neural impulse, and will send it to the brain. I'm going to skip this video. We're going to watch it in class. This is going to be a nice little animation of the whole thing, just walking you through all the parts. So, now that we have this idea of what's going on, we have to talk a little bit about how are we actually getting to the part where we're hearing. And this part is, again, kind of like our color conversation is a little bit up in the air. There's two main basic theories about how we hear. So we've got the place theory and the frequency theory. So the place theory explains how we distinguish high-pitched sounds because different parts of the cochlea are activated by different frequencies. So again, what you have to remember is our eardrum is only picking up vibrations. That's it. It's only picking up vibrations. So we don't actually and this is really, really complicated because you don't really hear, I guess, the way that we think we do. You really just pick up vibrations, and then we kind of create what it is. So the way that the place theory works is basically that within that cochlea, different parts of the cochlea, different places on the organ of Corti. So if you think about the shell, maybe like the middle part is one section, then as you go out, there's a bunch of different sections on the way out. And the way it works is basically that each of those sections is activated when different frequencies of water movement, or that fluid, I shouldn't say water, that fluid movement is going on in there. So only some parts would be being activated while others weren't. And the idea is that if some are being activated and some aren't, then that would make us able to hear all these different pitches and different sounds and different ways that we hear them. The other theory is what is called the frequency theory. So the frequency theory is basically the idea that the frequency of the auditory nerve impulses corresponds to the frequency of the tone. And so that's how we then detect pitch. So instead of it being different messages, basically, or different parts of our cochlea sending messages at different times, the frequency theory is just that it's the frequency of the messages. So how quickly are those messages being sent, those nerve impulses? How quickly are they being sent? Are there gaps? Are they happening really fast? And the idea is that just like frequency works, the different frequencies in the neural impulses would determine the different pitch of the sound. Okay, so those are the two things. Again, place theory is really focused on where the cochlea is differentiating between the different sounds, the different frequencies and sounds. The frequency theory is that our brain is really differentiating the frequencies based on the neural impulses, differentiating the pitch based on the neural impulses. Those are kind of the two main ideas there. So from there, we can start talking about locating sounds. And this is the picture I was talking about before, about how sound starts in one place and then goes outward. So you can see if this is my sound here in the corner, and then it slowly moves out. And these are these molecules, compressing and then spreading out and running into each other, basically. So one of the things we can look at is locating sounds. So this is an experiment we're going to do a little bit and mess with a little bit in class, where we are actually able to locate where things are based on the sound. So what happens is, and basically how do we do that? It's kind of the big question. So what happens is that when there's a sound wave and it runs into us, our ears, just like our eyes, are not in the exact same place. Right? You can see there's one ear over here, one over here. So there's a gap between the two. So what happens is the way that this wave will travel is depending on where I'm facing. So if I'm facing this way, it's going to run into one ear before it gets to the other. Now, obviously, this is going to vary on where you're looking. So if I'm looking directly at something, it might hit both ears at the exact same time. If I'm turned to one side, it's going to hit one ear first and then the other one after. So there's this gap in when those sounds are hitting my ear. And what's going to happen, again, just like our eyes, when we talk about our binocular cues, is our brain can then basically stitch that together. So because I heard it on the right side and then I heard it on the left side, I know that it's coming from over here. Now, our brain is also going to use parallel processing to kind of determine another way for us to identify where things are coming from as far as sound goes. So another way that we can do this is through what is called a sound shadow. So this is what it's talking about in this second bullet point here, where it says your brain processes both intensity differences and timing differences to determine where the sound is. So not only are we noticing the difference, or our brain is noticing the difference in, how long did it take to get from my right ear to my left ear, it's also noticing that it was louder in my right ear than my left ear. And so what's happening there is what's called the sound shadow. So when sound runs into something, every time it runs into something, it gets, that amplitude kind of goes down, right? It gets less loud, is the way to think about it. So what happens is it's not only do I hear it in my right ear first, it's also quieter in the left side than it was my right side. So again, both of these kind of things are being processed, the difference in the time and the difference in the amplitude of the sound. So again, my brain is going to process that all at once, and it's going to kind of spit out, it came from the right, it came from the left, it's right in front of me, or it's down or up, or whatever it is. So again, we're going to test this in class, so we'll talk about that then. The next thing we're going to talk about, this is going to be very quick because again, we're going to play this during class, is what is called the McGurk Effect. So the McGurk effect is one of the ways that we can look at the perceptual side of sound. And not only are we just going to look at the sound aspect, it's also ways that we can look at perception as it's involved with all of our senses. Because the reality is we don't really just use one sense at a time, right? We are looking at things and listening to things, and we are also feeling and smelling and tasting all at the same time. So the McGurk effect is actually an example of two different sensations coming in at once, and how we can mess with that to, again, mess with our perception. So what's going to happen, and basically I'm just going to tell you what the McGurk effect is, what's going to happen, and then we'll do it in class when I see you, is that there's going to be a visual and hearing illusion that basically happens at the same time. So they're going to give you a visual and an auditory stimulus at the same time. And what's going to happen is that the sound we hear is going to be changed by the visual picture that they show us. So this is going to sounds really weird before you see it. When we see it, it'll make a lot more sense. But basically the idea is that because I'm pairing sound and sight together, I'm basically able to either create a new third sound that I didn't actually hear, or I'm able to basically trick you into hearing something that you're not actually hearing. And so again, what's happening here is it's playing with how our senses work. Our senses didn't evolve on their own. We didn't learn how to see and then say, okay, that's pretty good, let's learn how to hear now. We did it all at once. So our hearing and our vision work together a lot of times. So what's going to happen is our hearing is looking for cues from our vision to help it out. And our vision is sometimes looking for cues from our hearing to help it out as well. And so because we know that, we can kind of mess with it a little bit and cause some of the problems, kind of like we did in our other illusions with visual perception. But again, I'll give you this example of the video when we're in class. So let's talk about our other senses here: taste, smell, and the body senses. So like I said, hearing is the next biggest one, and then we have kind of these ones that we really just won't go into as much detail about. Our first one is taste. Now the technical term for taste is gustation. Gustation. So taste is pretty simple, actually. Taste, when we taste something, literal chemical molecules from whatever it is we're tasting are going into the receptors in our mouths and on our tongues and in our throats, and they're causing the taste that we sense. Now we do have specific we do have specific sense like tasters, right? Generally we think of them as our taste buds. So obviously our tongues are, packed with taste buds. We do actually have them all over our mouths and actually in a bit of our throat as well. So again, those chemical molecules are literally just going in and connecting with these different tasters and causing us to have this sense of taste. Now there are 5 basic tastes. So everything we taste can be brought down to these 5 different tastes. There's sweet, salty, sour, bitter, and what is called umami. Umami is savory. So if you have a steak, that meat flavor is umami. So again, sweet, salty, sour, bitter, and umami. Now again, what's happening whenever we eat something, whenever we drink something, is that the molecules, like the literal pieces of what you're eating or drinking, are being broken down and dissolved, specifically like in your saliva. That's what chewing is for, is obviously to break down the food. Saliva actually breaks down your food as well. So it's breaking down those different things, and then it's interacting with the receptors in our tongue and our mouth and our throat, just like I said before. Now, one of the things that's really interesting is flavors actually are connected with different nutritional values, kind of essential nutrients, I should say. So I think I mentioned this before. We were talking a little bit more about evolutionary psychology, but basically we can look at these different flavors and we can connect them to things that we need. So for example, something that is sweet is going to contain sugar. So obviously this is talking about, in nature. So something that's natural in our real life and out in the world is like fruits. Fruits are sweet, and fruits are one of our better sources for sugar. Something that is, salt is something we need in our diet. So something that's salty is going to have that salt flavor, that salty flavor to it. Something that's sour or bitter can often be something maybe that's not good. So bitter, even though people drink stuff that's bitter and we like stuff that's bitter a little bit more now, same thing with sour, is they actually can connotate that something went bad. So it can give us a reason to avoid that flavor. Umami, again, is that meat, that protein flavor. So again, that's going to be something that we need. So the idea is that we taste these different things, and we can think of it the same way we think of vision, is we taste the way we taste because it makes sense to do that. That it allows us to be better about what we're eating. Today, it doesn't really work as well because we just go to Walmart and get whatever we want. But back in the day, it was useful because we'd go after things that tasted better, and if it tasted better, it could also mean that it was better for us. So it would help us kind of survive at that point. Let's look at smell a little bit. So smell is actually a lot more similar than taste than you would think. So smell is working a similar way as taste. The biggest difference is it's not going through the breakdown aspect where you're not chewing it and you don't have saliva that's breaking it down. But what's happening is with smell, or what is called olfaction. So anytime you see anything that says olfaction or olfactory, olfactory bulb, olfactory receptors, it's talking about smell. So basically what's happening is when you smell something, little tiny chemical molecules of whatever it is are going in your nose. That's how it works. That's why when you spray like Febreze or deodorant or suntan lotion or bug spray or whatever, you smell it really well. It's because those little tiny pieces are literally just going into your nose and you're smelling those. And it's picking up those chemicals. So they're binding with our olfactory receptors, all these little guys right here. And then that goes to our olfactory bulb, So again, entering the nose, bonding with these hair-like cells, olfactory receptors here. There's a whole bunch of chemical stuff that's going on that we don't really care too much about. Goes to the olfactory bulb, and then that's going to get sent to the limbic system. Whoops, and I covered it up. And I believe it's the primary olfactory cortex, which again, we didn't really talk about, something we don't really care too much about for our class, for our purposes. So very similar to taste, just happening a little bit different place in a little bit different way. We're going to do a test where we talk about taste and flavor. Taste and smell and flavor, and we'll kind of get into that in class as well. We can also talk about pheromones. Now, this is less of a big topic for basic level psychology and for human psychology as it is for like animals. So some of the stuff we see in here is going to be more connected to that because psychology is still a study of animal behavior as well as human behavior. So sometimes we'll see things like that. So pheromones, for example, what they are literal airborne chemical signals that animals use to interact with each other in some way. So what they're there for is to provide information. Now, usually it has to do with information about reproductive status of a potential mate. So this is why you'll see animals going around and they're smelling for each other. Right now, it doesn't necessarily mean that every time an animal smells another animal, they're trying to see if they're going to mate, but they're looking for information. Our noses, again, don't really work on that level, so we don't quite have the same kind of pheromonal stuff going on as animals do, where you talk about like when animals get in heat and when they mark and do those things, it's because they are putting that information out. It's because that's how they're going to interact with each other. What it's going to do, so a pheromone scent triggers illicit emotions in the hypothalamus, such as attraction, sexual desire, and arousal. So the idea is there's these literal chemical signals that are in these animals that they're able to produce and then release, and those things actually trigger these different reactions in the hypothalamus. Now again, I think human beings technically have some level of pheromones, but again, it's not the same as animals. It's not like a message. We don't go around smelling things to find a mate. But that's just kind of a more broad topic. So let's talk about touch a little bit. So our touch and bodily senses are kind of connected a little bit here, but we're going to pull them apart to look at each one. So when we're talking about touch or feeling of touch, we're talking about the somatoesthetic sense. Somatoesthetic sense. It's kind of a little hard to say there. And it should make sense when we talked about the somatosensory cortex. This is the sense that's connected to it. So the senses of the skin. So this is allowing for the feeling of just touch, like when you poke something or you feel something, pressure, pain, cold, and warm. All of those senses in our skin are going to be what's considered the somatoesthetic sense. So inside of our skin, and we actually have this in one of our coloring book pages, you don't necessarily need to know all the parts, but if you want to, it's pretty interesting. There's a whole bunch of different kinds of cell receptors all over our skin and inside of our skin. So again, some of them are looking for cold, some of them are sensing heat, some of them are sensing pain, some of them are sensing like something like pressure, some of them are sensing texture, and all of them again are collecting data all the time, sending it up to our body when we need it. So all that information is then going to go up. This is an image of what is called the homunculus. So the homunculus is a human being if we were the correct size based on the amount of somatoesthetic sense in each of our body parts. So that's why we have giant hands and really big lips and tongue, because that is where the vast majority of our touch senses are based, which makes sense. Again, we obviously are using our hands for the majority of things, so we want to be able to have really good sense of touch in our hands compared to our elbows that, you know, we don't really need to feel that well in because we don't use them that much for that. Again, we're going to test our touch in class as well. So let's talk a little bit about pain. Now, we're not going to go super deep into it. There's a lot more to talk about here. We're really just going to talk about what is it, and then we'll talk a little bit about gate control theory of pain. So pain, probably something you already knew, is the body's warning system. It tells you that something is wrong. So this is why pain is super obviously important. Otherwise, you could like light yourself on fire, and if it was, you know, behind you, you wouldn't even notice because you wouldn't feel anything. It wouldn't hurt. Same thing when you pull a muscle or something. It's important that your body knows right away that something's wrong. That way you can, do whatever you need to do to fix it. So pain is a very important sense. It's our warning signal. So let's talk a little bit about the gate control theory of pain. So the way this theory works is that there is this metaphorical gate in the spinal cord that switches pain on and off. Now again, it's not like a literal gate. It's more of kind of like, I like to think of it kind of like a switch. And what's going to happen is that can be switched on or off depending on what is going on in the body. So, for example, the more neurons that are firing in response to pain, the more intense the pain. So what can happen here is this idea that basically the bigger the problem is, the more pain, the more neurons are going to be firing, the faster they're going to be firing, right? That gate is going to do different things. And in addition to just what it's going to do immediately, so let's say I fall and I hurt my knee, it's also going to affect how we experience that pain later on. So it's not just necessarily in that moment, but also later. So for example, and I'm sure you guys have seen this with little kids especially, you may have hurt yourself before, but then if you distract yourself, all of a sudden that pain goes away. So this is again with little kids. If you've ever seen a little kid fall and skin their knee and they're crying and everything's horrible, right? And then you stick a Band-Aid on it, or you kiss it and you're like, oh, it's all better, and then they're fine and everything's okay. Once we distract them, that pain can basically subside. And you've probably noticed this in your own life. You may have had maybe your back hurt or, something was just bothering you, but then you had something to do, so you started working and all of a sudden you kind of forgot that it hurt, kind of went away. So there's a psychological influence that we can see when we're distracted from pain. In addition, obviously, we can soothe pain through the release of endorphins. So we've talked about endorphins already, these natural painkillers that go out and basically help kill that pain. We can also use other biological things. This is why acetaminophen and ibuprofen and morphine and Oxycontin and all these other drugs exist, is to basically dull these pains. So there's a lot of different kind of ways that pain can be experienced. It's also different for everybody. People have different types of pain and different pain tolerances. So there's a lot to kind of talk about. One thing too that would be connected to gate control theory is you may have, I don't know if you've ever heard this story. I think this was in Colorado where it happened, but there's really crazy stories about people where they like fall. The example I'm thinking of is this lady, and she was hiking and she fell like off a cliff. And I can't remember exactly how far, but she fell off a cliff and she broke, I think she broke her collarbone and her arm and 3 of her ribs and her leg or something like that. So she like basically just like destroyed the whole side of her body. And she got up and walked like, I think it was 5 miles with all of that damage. And the second she got rescued, she passed out from the pain. And when they were talking to her after, right, she was talking about how in that moment, she actually didn't feel the pain. And now what's going on here is a whole bunch of things, right? There's the psychological aspect of knowing that you need to survive, that you have to get somewhere, you can't just lay there. There's the endorphins that are obviously killing that pain. There's the adrenaline that's getting your body up. And then we could also say that there's this idea of this gate that can say, okay, right now we need to switch this pain off. Right now our body knows something's wrong, but there's too much pain that's going to overwhelm us. So that's why we see where people do really, really crazy things. Another example that's not as crazy as the one I just gave you, but when I was in high school, I was like a freshman, and our football team was playing the state championship. And one of the kids, we were losing, and it was the last play of the game, and they handed it off to him or whatever, and he ran like 60 yards and scored a touchdown. You know, and everything was fine, went over, and he like walked over, and he found out the next day that he broke his foot during that play and didn't even notice. And again, what was going on was there's all these other kind of influences that were basically causing that pain to go away, and he actually had gotten stepped on like the first like 2 steps of the play and just didn't even notice it, even though it had like broken a few bones in his foot. So there's a lot of kind of like different things to talk about and look at with pain here. So that's going to get us to our bodily senses. So there's 2 main bodily senses, kinesthesis and the vestibular sense. And we're going to look at both of these as well. So kinesthesis is, I'm just going to read it right off here, the system for sensing the position and movement of the individual body parts using sensors in your joints, tendons, bones, and ears, as well as your skin sensors. So this is how our body knows where it is in relation to itself. So when you move your body, and again, we're going to do a little bit of an experiment here. When you move your body around, if you close your eyes right now and start moving your limbs, you don't have to open your eyes to know where your limbs are. You can feel it. You can feel it in relation to each other. That's why you can do something. That's why people can do like no-look passes and things like that, because they don't have to be visually seeing what's going on. We have sensors in our limbs that can tell us where everything is. So that's kinesthesis, this idea of knowing where our body is in relation to itself. We also have what's called the vestibular sense. So the vestibular sense is actually fluids in our ear. And actually, let me see if I can go back. Can I go back and show you them? I can actually show you where they are. Right here. So these little tunnels right here, these little like snail tubes, little curly Q guys here. Those are in our ear canal, and they're filled with fluids. So what happens is when we move around, those fluids move as well. So if I'm upside down, those fluids all of a sudden start running up towards the top of my head. When I'm sitting down, they're running here. When I lay backwards, they're there, right? So as I move around, that fluid sloshes around with me. This is why when you spin around really fast, you get dizzy. Because what happens is I'm spinning. When I stop spinning, that fluid in my ears is still moving. It's still moving around, and that's why you get that dizzy thing where you don't have good balance. It's our vestibular sense. So what's happening here is, again, it's our head is basically monitoring its position in space. So this is what allows people to do things, right? Be upside down or backwards or whatever, without necessarily needing to be able to like see or know what's going on. The example, and we may or may not watch this in class. One of the examples here is actually this guy here. We see this in wrestling because it's one of the very few sports that we actually have blind competitors in. And some of them are actually very successful. I believe the guy that in the video they talk about actually made it to state that year. And they actually can be pretty successful. Now, there are a few little changes in the rules, like you have to remain in contact with them at all times, but they're still able to wrestle and move around even though they can't physically see their opponent. Basically what happens is they use these two senses to understand where they're going to be. So they have their own vestibular sense to tell them where their body is, and then they can use their kinesthetic sense to tell them, okay, where are all my limbs, and thus where is my opponent's limbs? Where is their body parts? And how do I move them and then move to them and on and on. So basically, again, how these two are working together. Again, we're going to do a little bit of a test. This one we might not be able to do it in class, but I'm going to try and show you, hopefully. The last piece we're going to talk about, again, we'll watch this together, is synesthesia. Synesthesia. It's actually a pretty simple definition. It's very, very interesting, though. So basically what it is where, for some reason, in certain people's brains, there's connections that normally aren't there. And what it does is it has connected different senses together. So what happens is they experience a sense in two different ways. So for example, they can see colors, right? And that's actually what we see here, where she paints music, because when it plays, it does not just sound like it is for most people. She actually sees the color of that music. There's basically kind of like a cross wiring of her senses going on. So that's synesthesia. Again, it's when one type of sensation activates more than one sense. And there's a whole bunch of different types of it, but we'll just look at one in class. Okay, so that wraps up everything for our sensation perception unit. Take some time and do a quick summary. This one might be a little longer. It's a little longer of a section to wrap up, and then I will see you guys later.